Okay, hello everyone here and online. Welcome to the March 6th, 2025, first Thursday program for this month. I'm not Lisa Spence. You might have guessed I'm Stokes McMillan. Lisa's traveling the world right now. So today we have as our speaker Dr. Timothy Macaulay. He's the director of JSC's Neurosciences Lab. So let me give you a little bit about him. So Dr. Macaulay is the Neurosciences Lab Director in the Biomedical Sciences branch and here at JSC. And so the lab supports multiple NASA programs via scientific investigations, technology development, and operational activities. Research is conducted with astronaut crew as well as ground participants in spacecraft analogs such as head down, tilt bed rest, and sustained centrifugation. The lab specializes in characterizing and mitigating the spaceflight risks of shared sensorimotor vestibular function impacting crew health and critical mission tasks. So Dr. Macaulay, or Tim, he earned his BS in physiology and neuroscience from the University of California, San Diego, and he has PhD in biokinesiology from the University of Southern Cal. So let me turn it over to Dr. Tim Macaulay. Tim?
Thank you. Thanks, Stokes. Thank you. Thank you all for being here today. Online, can you confirm you can still see the slides? I'll take that as a yes.
Yeah, go ahead, run your slides.
Okay, great. Yeah, so thank you for that introduction, Stokes. I did hear that this was going to be a kind of an interactive presentation, so feel free to stop me at any time. We can be kind of informal, just ask questions. Happy to go into detail on any of the research that we do or the different analogs that we use. Just let me know. Happy to answer any questions. Okay. And also, I think you mentioned this group is interested in more of a technical talk. So I am starting with a bit of background on sensorimotor and vestibular physiology. So just a quick overview, but again, we can go into detail on anything you guys are interested in. So as the neuroscience lab, we are primarily interested in how these three sensory systems are used. So visual, vestibular, and somatosensory functions, how they're combined in the central nervous system for the control of movement, right? And this is a continuous process. So in normal, healthy adults, in 1G, we're always getting new information from, our vision, from vestibular system, and from our senses of touch and pressure. And those are continuously used to control movement. In addition, at the same time, we are predicting what sensory cues we're going to experience based on movements that we do and the environment around us. And we're always comparing the sensory inputs that we receive from these different systems. So what's important is that this works very well. It's a very strong, redundant system in 1G that we're well adapted to. What happens, though, with crew members when they transition to a new gravitational environment is that you get discordance or conflicts between the information you get from these three different systems, and or you get differences in the sensory inputs you predict versus the sensory inputs you actually receive. And so that leads to a lot of the issues that we're going to talk about in some of the later slides. So it's important to note, this is a learned ability, like I have here at the bottom, to interpret these continuous sensory signals. And so when you go into a new environment, you need to relearn or reinterpret these signals. And of course, the main transitions that we're concerned with are, going into microgravity and then coming back to Earth. But now with exploration missions, there'll be additional G transitions and additional environments that are novel to the crew members. A little background on the vestibular system. So there's two major parts. We have the semicircular canals, which have fluids in your inner ears that kind of measure different angular rotations. So it's angular changes in all three planes. That one doesn't actually change that much with spaceflight. But the other one we have is the otolith organs. So basically you have these crystals that sit on hair cells, and they measure linear accelerations, which include gravity. And what's important too is that there's this ambiguity between tilt and translation when we're on the ground. So you can see this first figure here. There's always in 1G going to be the downward acceleration of gravity. When you tilt your head, there's this shear on the otoliths, which tell you your head is tilted relative to gravity. Okay. But you can also get translated, right? And it can cause that same shear to the otoliths. So you can see here in the second picture, you still have that downward 1G, but now you have that shear of the otoliths, which simulates the same shear you get when you tilt. So that's sort of how some of those simulations work, those rides you might have been to at Universal Studios or Disneyland, when they're not really a roller coaster, they're just kind of tilting you to give you that sensation of being accelerated or tilted. Yeah.
Quick question.
Yep.
You probably have to repeat it here.
Sure.
I know with those, I can't pronounce it, but those little airs or like that, calcification can happen that people cause them to feel dizzy and such.
Yeah.
Is that more prevalent to happen in space or less happen because of just the motions that are available there in space?
Yeah, so we actually don't have direct evidence of that in humans right now. We do have animal evidence of that. And so it's something that we have a current study right now. It's our vestibular health study, where we're testing astronauts in flight and post-flight at multiple time points to try to better characterize their vestibular adaptation and to determine whether these changes are due to more central adaptations versus peripheral in the actual sensors that you're talking about. But so we don't have the data yet. It is possible, from the animal research, that those calcium crystals, the otoliths, it is possible that they are getting dislodged or that they get calcified and kind of clumped together. But again, it just hasn't been demonstrated yet with humans.
Thank you.
And it's a little difficult to measure.
Hey, Tim, if you could repeat questions for Zoom. We can't really pick up the questions too well in the room.
Yeah, sorry about that. The question was basically, have we seen some of the changes to the actual vestibular system itself, the peripheral structure of it? And the main answer there is no, we haven't been able to measure that directly yet. Okay, so those top pictures were for 1G environments, but in 0G, right, there's not the constant downward 1G acceleration, and there's no such thing as tilt in 0G. So when you tilt your head in 0G, you don't get that shear with the otoliths, right? But you can still get that shear via translation. So one of the things that we'll see in some of the later slides is there's this reinterpretation of those signals. So when you get that shear in the otoliths, you tend to always interpret that as being translated rather tilting relative to gravity. So that does lead to issues when astronauts return to Earth, of course. And one little quick test that can help you understand what all of this helps you with, if everyone can please look at their hand, pick a point on their hand, and then move your hand back and forth and try to focus on that point. I'm assuming it's pretty blurry. It should be. Okay. Now keep your hand still and move your head at that same speed while you try to look at your hand. What should happen is that the point on your hand should be more clear now than when you were moving your head. Okay, so that's your vestibular system, and that connection between your vestibular system and your eyes, helping to control your eyes to focus on that point. That's just one of the things that your vestibular system helps to do and can get disrupted in flight. This is a list of all the other impacts that these vestibular adaptations can have. So it, all comes to the vestibular nuclei, and then, it can lead to issues such as motion sickness, gaze disturbances, disorientation and motion, illusions, spatial memory and navigation deficits, ataxia, and head-trunk coordination and postural instability. So we'll see more of the specifics of what we've seen in astronauts in a bit. Okay, the other main sensory system to mention here is the somatosensory system. We are primarily interested in the ones circled here. So it includes touch, pressure, joint position and movement sense. And why those are so important is because, in 1G, they can help provide a reference for your body position and movement in space. And in a lot of cases, it does have a lower threshold for those movements compared to your vestibular inputs. So for example, if you were to stand, with your eyes closed in a single leg balance task, those sensations of touch and pressure on your foot, those sensations of muscle activation in your legs, those would help you detect your sway more quickly than your vestibular system is. And so it helps you prevent a fall, for example, when you're in the dark. Okay, so that was just a quick physiology review. This is the definition of the risk that we're responsible for, sensorimotor risk. As I mentioned, it primarily has to do with changes in gravity, and it can lead to several different complications such as listed here: motion sickness, spatial disorientation, decrements in postural control and locomotion, and fine motor control deficits. And we're really interested or concerned with how it can impact spaceflight operations, such as manual control or taking over a vehicle during landings, early EVA that can require posture, balance, coordination, and it can all be in a novel gravitational environment. And then last to mention is crew egress, which can require all of those things mentioned before, but it could also be in a very time-critical emergency environment. Unfortunately, the adaptations, the disruptions due to the adaptations are the greatest during and immediately after G transitions. And that also happens to be when these operations are the most critical. So you can see here that the relative risk from these changes is highest, during these periods when operations are the most critical. And with exploration missions, we're going to have additional G transitions. So, the first one being launch into orbit, and then landing on a planetary surface, launching back into transit, and then returning to Earth. So, typically when you just go to the ISS, there's just a G transition going up and then coming back down. But now with 4 G transitions in exploration missions, we think that the risk is going to be much greater. And just to clarify something, so these adaptive changes to sensorimotor function are good. We do want people to adapt to their new environment. It's just that during the period of adapting to their new environment, there are disruptions that we'll see in a second that leads to these risks. And that's what we need to help either help mitigate those disruptions or help them adapt more quickly to their new environment. Yeah.
My experience with training pilots is some folks tend to be very tolerant of motion sickness. Some adapt after a lot of flights. They don't seem to be as intolerant, and some don't ever seem always seem to be very intolerant of spatial disturbances like that.
Yeah.
What's the experience with the astronaut population?
Yeah, so the question for those online was about the different variability between pilots in how they experience motion sickness and what is the experience with astronauts. So the motion sickness that's experienced on the ground is typically not well associated with motion sickness experienced in flight and post-flight. That makes it very difficult for us because then we can't really predict whether an individual crew member will be susceptible to space motion sickness. And it's very surprising, actually. But there is a lot of variability as well, which makes it difficult too.
So is there any training environment that's possible on the ground that you can do, the Vomit Comet, or, these 3D ball tumbling kind of things is there any way to train people to be more adapted before they actually fly?
Yeah, so parabolic flight, surprisingly, motion sickness during parabolic flight is also surprisingly not correlated with in-flight and post-flight motion sickness. So that is surprising to us as well. Sorry for those online if I didn't repeat the question, but it was basically asking if there are any good ground predictors. And actually there is one that I haven't mentioned yet. It is hypergravity centrifugation. So a lot of this work has been done with some of our colleagues over in the Netherlands. So they'll spin people up for an hour at 3GX, and that has actually been one of the best predictors of space motion sickness because they've done it with astronauts and had them do the same type of head tilts after the 3GX centrifugation and after they get into space. And some of the vestibular responses are very similar between those two situations. I think there's just a big operational implementation issue there, given the large hardware you need to have a whole centrifuge and the expertise you need and medical and safety to run that centrifuge. So yeah, to our understanding, no one is really using that right now.
We got rid of ours because we didn't think it was useful.
Yeah. So, but really, that's the best that there is right now. Yeah. So speaking of motion sickness, these are some early data, but about 80 to 90% of shuttle crew members experience some symptoms of space motion sickness, and this is just kind of experience any type of symptoms. So most people experience some symptoms. To the level that it actually starts to impact their performance is probably more around 50% of crew members. But again, there's very high variability, very hard to predict who the individuals will be. Yeah.
Any similar data from Soyuz or from Dragon?
The question was any similar data from Soyuz or Dragon? The answer is yes, and that's why I just kind of summarized it here with the shuttle data. It's all pretty similar. There are some differences based on the vehicle size. I don't quite know why that is, but it's not that different. It's more just this general variability between different crew members. Symptoms generally last 2 to 3 days in flight. So you can see in this graph, it kind of peaks maybe 10 to 12 hours after being in a microgravity environment. And then the decline as they adapt to their new environment, the decline is pretty rapid. So after, a day or two, those motion sickness symptoms go away pretty quickly. Also in flight, we see some other disturbances in gaze control and spatial disorientation. So for example, crew members can feel continuously inverted, and they can feel especially sick when they see, one of their fellow crew members floating by them upside down. And so this can be kind of a recurring problem. They, just see different illusions based on not having a straight up and down environment or reference. We also see changes in eye-head coordination and smooth pursuit and vestibular ocular reflexes. So for example, in these data that you see here, it's a target acquisition task. So crew members were asked to move their heads and capture a target that was projected on the wall. And you see pre-flight, they're able to nicely coordinate their head movement and their eye movement in order to capture that target pretty smoothly. But then when they were doing this on flight day 2, in flight, the eye movements had been infused with several saccades. So basically there were all these small adjustments that were being made to try to focus on that target. And that is likely because of that, vestibular disorientation.
Okay. Tim, we have a question online about MIT and others experimenting with dancing to help combat orthostatic intolerance, maybe something called pivots, maybe a temporary prevention that would go away when dancing and spinning training stops.
Yeah, so I'm not familiar with that specific dancing countermeasure or that group, but there have been several different kind of adaptation or rehab techniques proposed. So of course, you don't want the crew members moving their head really fast once they get in flight. That will just kind of aggravate the symptoms and likely lead to motion sickness. But you also don't want them to kind of lock their head in space and not, adapt to the new environment. So what our lab is actually working on right now is more of an incremental head movement approach to get them used to the new vestibular inputs in their new environment to help them incrementally adapt. So I imagine, something like a dance or different movements like that can do something similar. Yep.
The games, 3D virtual reality games, are kind of notorious for giving people motion sickness.
Yeah.
Is this a similar effect of what you're seeing, a conflict between what your eyes are perceiving and your other sensors are feeding in that conflict?
Yep. So for people online, the question was about VR and what the mechanisms of VR motion sickness are. And yeah, you're spot on. So similar to what we're talking about here is that there's this conflict between what your vestibular system is reading from your movements in your environment and what your eyes are seeing from the VR environment. So if your eyes are seeing that you're tilting or you're tumbling, but your vestibular system is not sending those same signals, then there's a conflict, and that can lead to sickness. So it's similar idea. Okay, there's also changes in proprioception. So for example, changes in how well someone can move a mass or an object in space and how accurately they can move that object. There's also changes in how well they can reproduce arm movements or reproduce angles or point to objects when their eyes are closed. And one thing to point out is that, with the vestibular system, we think of more of like a one time you need to adapt to this new environment step change from, 1G to 0G. Versus for proprioception, you still have that kind of adaptation to your new environment. You need to now calculate your arm movements so that you're not moving against gravity anymore, right? But then there's also this deconditioning component with proprioception. We know that there's muscle loss, there's changes in strength, there's also changes in how well we're able to sense where our limb positions are because we're not used to using those senses while we're in flight. We're not used to having to load our feet and our legs while we're in flight, because we're not standing and walking around in flight. We're kind of floating. So keep that in mind. There's kind of those two components, the adaptation and the deconditioning. Okay, so those data were for in-flight. Now let's talk about return to Earth. So typically those, the severity of those disruptions that we just discussed are pretty mild, maybe moderate early in-flight. What we actually see post-flight, though, is that the disruptions are more on the moderate to severe level. So that's what's here on the y-axis. Crew members reported severity of impacts to functional tasks. And you can see a level of 4 here is severe, meaning that tasks weren't attempted because they might have been feeling too sick, too disoriented, felt it was unsafe, or they just deliberately restricted their motion, such as just wanting to kind of sit in a chair and relax or whatnot. So here's an example of motion sickness data. On the y-axis is just a basic rating of motion sickness severity on a scale of 0 to 20, 0 being no motion sickness, 20 being vomiting, 10 being halfway to vomiting. Again, you see this very high variability between the different crew members. Again, makes it very hard for us to develop countermeasures and whatnot. But what we do always expect is to see this very fast decline in motion sickness severity. And that's what you see here. After a day, day and a half, most of those motion sickness symptoms are pretty much gone by then. We also did separate here in green the crew members that were on Soyuz missions, and then in blue, those that landed in the water with Dragon landings. We originally were very concerned with the water landings potentially causing more motion sickness because of the wave motions. But what we see here is that there's actually no difference between the green and the blue. And that's primarily because SpaceX and NASA have just done a really good job of scheduling for very calm sea states. They constantly are pushing the landings by, a day or even a couple weeks to get very good weather and very calm sea states. We think that's been very helpful, but it does mean that we still don't really know the risk if crew members land in higher sea states or more inclement weather conditions.
You're saying adapting to 1G goes much quicker than adapting to 0G?
Not necessarily.
Well, here it was like a day and a half. 0G, I thought you said, could 2 days, could even be over a week.
Yeah, so there are other adaptations going on as well in flight, since it's a novel environment and there's the constant headward fluid shifts. So part of it could be those interactions with, say, the headward fluid shifts causing congestion in their head and causing other problems. But again, there's just so much variability there. Okay, so a big risk that we're concerned with right now is manual control. These data are from shuttle missions. So if you can see the colors in black, it's the performance on shuttle training aircrafts doing this vertical velocity at touchdown, during a simulated landing. In blue is that same measure on the actual landing of the shuttle mission. And what you can see is that much more of this cumulative distribution function falls outside of the desired range and more into the acceptable range. Luckily there were no real accidents, but it is still an increased risk of falling outside of that desired range.
Question.
And yeah.
I can't remember what the astronaut's last name is. His first name was Kevin, I know that. But he basically said that the control laws set up on the shuttle were not as intuitive as you would have on, let's say, a 737 today to be able to land. How much do you factor in the complexity of the vehicle itself and how to fly it.
Yeah.
And how it is different. I know you're using the shuttle, training aircraft, but it's still a very different kind of thing. You can't really compare the two necessarily 100%.
Yes. So the question is about vehicle complexity and how that factors into the risk. It actually goes even further now. So we're still very concerned with the manual control risk and having to take over a vehicle for landing on the moon or on Mars. There are many people that believe that it shouldn't be a risk at all if we take the human out of the loop. If these landings become completely automated, so the human has no control, no ability to take over the vehicle landing, then this manual control risk would go away, because they have no way to impact the landing.
Let me ask the question a little differently.
Sure. Yep.
With let's use the 737. It was very intuitive to fly. The shuttle, they had to learn to fly because it's different than normal aircraft, what they understood.
Okay.
And so that translation has to happen in the middle there.
Okay.
And so using shuttle data, is that a factor that maybe skews the data a little bit one way or the other, or is it true independent of the vehicle you were actually flying?
Yeah. For those online.
I know it's just, we worked a lot of that on Orion and OSP and SLI. We had to debate all those things. Again,
yeah.
Whether to do automated versus manual control.
Yeah. Yeah. The question is basically about how we use these data from shuttle missions and extrapolate going forward on vehicles that might have different levels of difficulty, different levels of intuitiveness to control. And that kind of leads to a question of, there's a skills-based component. So we do want to have countermeasures for manual control that are more skills-based. So even if it's not as intuitive of a machine, can they practice on that so much so that it becomes second nature to them? But there's also this disorientation component. So there is this concern, no matter how much you practice on it, you can still show disruptions. And actually, so this next slide will be a good example of that, because driving will be a little more intuitive for us to all understand who aren't pilots. And it's something most people would think that your skills are probably so good at driving that you would maintain those skills after you come back from 6 months of ISS missions. Therefore, any changes in your driving abilities are more likely due to these, sensorimotor disruptions. So what you see in this video on the left is pre-flight, on the right is post-flight. You can also see it in the figures on the right. So the middle white line is the lane divider in both of these, and then the red squigglies are the actual position of the car. So obviously you want to keep your car on the correct side of the lane divider, and that is what the crew member in this example was able to do pretty well in this top one. Side note, this is meant to be a more difficult driving task where they have to, go on a winding road pretty quickly. Post-flight, what you see is that they're spending significantly more time in the wrong lane, which was our measure of driving performance. So in this data set of ISS crew members on R+0, they spent significantly more time in the wrong lane compared to pre-flight. And then, it mostly recovered by R+4 and R+8. One thing for us, though, is that what we're calling R+0, we really didn't get them back to JSC to do this driving simulation until 24 hours after they landed. And we think a lot of that recovery happens in those 24 hours. So what we really need is to get some manual control data much sooner after they land. And of course, that is difficult because you need a whole motion base and whatnot to really simulate some of these vehicles. But we do have an ongoing study right now to better characterize this. Yep.
Do y'all prevent the crew from driving for a few days after they land?
Yes. Yeah. It's we don't have a hard criteria right now, but typically they work with their flight doc, and usually it's about a week. Yeah. Okay, so now let's talk about functional performance. So, these are things like activities of daily living, standing, walking, balancing. And again, the impacts are going to be highly variable between crew members. You'll see some examples of that in a second. And it's, possibly greater impacts with longer durations of spaceflight. I also just want to mention, they're not just experiencing these changes in balance, but they're dealing with motion sickness. They're taking medications for that, which have side effects. They're dealing with cardiovascular changes. They're dealing with fatigue. All of these different things. This is a kind of just a summary of what we kind of expect based on some decades of data that we have. So on the y-axis, it's the percent of crew that are performing at their pre-flight level. On the x-axis is the number of days since landing. And what we see is, on the day of their landing, we expect basically none of them to be performing at their pre-flight levels. But depending on the complexity of the task, they can be performing at pre-flight, with simple tasks like, standing up within, a day or a couple of days. The more complex the task, the longer it likely will take for them to recover. So for something like a tandem walk, which I'll show you a video of in a second, it can take several days or even, a week or more. And I mentioned before, a lot of this adaptation happens very quickly. So we do try to send our operators out to landing sites to try to collect this data as soon as possible after the landing. Okay, here's some examples of crew members post-flight. So these are all ISS crew members. This first one is 12 hours after they landed. They're just asked to go from that lying down position to standing up as quickly and as safely as they can. What you probably notice is that it's taking a little longer than you would expect, if they were just a normal, healthy adult. And also right there, they take a little step, a little recovery step. So, this is okay right now, given that, they're landing on Earth. They have a lot of recovery personnel, medical support. But of course, if they didn't have all of that support, or if they were on a planetary surface in a novel gravitational environment, then this can be a concern. The next one is a tandem walk task. So it's a little more challenging, but we ask them to kind of walk in a heel-to-toe fashion with their arms folded across their chest and with their eyes closed, kind of like a sobriety test. And this crew member is 1 hour after landing from a Soyuz landing. And you can see that they're basically being held up by the spotters, by the operators there, keeping them from falling. The last one is a finger to nose test. So you might have done this with your doctor before. You just start with your finger on your nose and you reach out and touch the doctor's finger. You're controlling degrees of freedom at your shoulder, elbow, and wrist. Typically, we're able to create a straight line trajectory and accurately touch the finger. But what you see here is that the crew member is, kind of shaky. They're not moving in a straight line, and they sometimes miss the fingertip. So you can imagine if this were, an operational scenario and they needed to touch a certain button in their vehicle, if they miss, that could be, that can cause some problems. Okay, so here's some actual data associated with the tandem walk task. So the same kind of heel-to-toe stepping that you saw earlier. On the y-axis, it's the percent of correct steps. And then on the x-axis, you can see first pre-flight and then post-flight number of days, starting from 0 going out to 12. So for all of these different functional tasks, we basically expect to see this kind of rapid relearning when they land back on Earth. And then there's kind of this slower readaptation in the next several days after they return and after they start readapting to Earth's gravity. So that's the typical recovery curve. I won't go into too much detail on this one other than just to say that this is basically a medical balance test that you might have seen in clinics before. And we just have decades of data on this because it's one of our medical requirements. So most of the crew members do this one. And basically what you can see is that it follows the same kind of pattern of this rapid relearning and then a little bit slower readaptation. And it differs a little bit by which condition of the test that you're using. Some of the conditions are more challenging than others. Okay, so I wanted to talk a little bit about how our research right now is trying to inform some of the Artemis missions and Martian missions beyond that. Yeah, question.
So, you've got some high frequent flyers now.
Yeah.
Who've been up and down, long duration, multiple. What kind of data are you seeing? Their first adaptation, their second mission, their third mission? Is there any learning or any statistical correlation to the more you do it, the better you get at adapting to 0G and then readapting to 1G?
And on that, just that, so it's with long duration versus small durations.
Yeah. So the first question was about looking at crew members that have gone on multiple flights, and are they getting better at adapting? Actually, it's more that their performance and their adaptation on the previous flight is a very good predictor of how they'll do on their subsequent flight. I don't think we have enough data to show that they are starting to get better with more flights, but it does just help us better predict where they'll fall on that, very highly variable spread of data points that I showed earlier. More likely they'll be similar to how they looked in their previous flight. And then the question was about a lot of short durations versus some long durations. So we do have some data. You can see here the green compared to the red, where after short duration missions, the recovery actually seems to be much quicker compared to longer duration missions. Part of that is likely because, as I mentioned before, there's kind of this adaptation part where you're just adapting to your new gravitational environment, but then there's also this deconditioning part. So the longer you're in flight, the longer that deconditioning happens, and the longer you have to recondition when you come back to Earth. So this is some of our best data right here on comparing short versus long duration.
How does the Russian experience compare with this?
We have teamed with the Russians for some studies. So I don't think I have any data in these slides, but if you've heard of the field test study, that study, we collected data about 3 or 4 times on the crew member. It was like the most frequent post-flight data collections that we've done with crew members, because we collected them first in a tent right out of the Soyuz, and then a few hours later at a local small airport, and then we tested them again when they got either back to JSC or back to Russia. And so they look similar to us, to our crew members.
Flight been with the Russian counterpart, anything there?
And they're specific.
The 1 year, were they compatible or comparable?
The question is Scott Kelly and his Russian counterpart, did they look comparable? I don't know off the top of my head, but that study was published so openly and stuff. I'm sure we could find that information. But a lot of times, looking at specific crew members, there's a lot of subject protections, data protections. Okay, so for Artemis missions, I mentioned before, we have these additional G transitions. We have novel gravitational environments on the moon that they need to adapt to. But, we also want to point out that there are some novelties to Artemis missions compared to the previous Apollo missions. So, for example, the transit to the moon is likely going to be much longer now. So previously it was about 4 to 5 days, and now it's looking like it's going to be closer to about a 12-day transit to the moon. Previously, they stayed on the lunar surface for 1 to 3 days, but now it's looking more like 6.5 days on the lunar surface. And previously they might have done, 1 or 2 EVAs, and, they might have been a few hours each. But now the current plans are to have 4 lunar EVAs each mission, and each EVA is looking to average about 5 hours each. So all of these kind of raise the risk of experiencing some of these disorientations, disruptions, leading to like a
So Artemis
fall.
basically is trying to get back to where the shuttle was. In effect, it was 5 hour EVA. It was pretty close.
Okay, yeah. They're planning to do a lot of geology sampling and a lot of EDA hours.
Okay. So Tim, we have another question online.
Yep.
So after decades of spaceflight, we know more and more detail about the pathophysiology of neurovestibular MAL adaptation to the environment. However, what have we implemented as potential countermeasures other than CNS depressants, e.g. compazine or phenagran? Don Parker from University of Miami in the late 80s proposed some pre-adaptive training, but it didn't go anywhere. Has there been anything else?
Yes, good question. So I didn't hear all of those that you mentioned, but it sounded a lot of those were motion sickness medications. So we do have several that are offered to crew members and are used pretty regularly right now. So that is good. I mean, there's still a lot of debate on what the optimal dosage is and timing of those medications, but they do seem to be helping. Otherwise, one of the best sensorimotor countermeasures right now is just exercise. And, we know that it's primarily targeting muscle and strength and aerobic capacity, but it actually is a very strong sensorimotor countermeasure as well. So if we look at our data, there was a big change in balance performance when, there was the addition of the treadmill, and when there was the switching from the IRED to the ARED, for example. So with the exploration missions and having less in-flight exercise countermeasure capabilities, we do think that's an additional risk for the sensorimotor risk. And that actually is going to be one of the slides I was going to show. This is a in-flight balance training countermeasure that we're developing, because if we don't have all of those in-flight exercise countermeasures, then we do need something to help supplement for sensorimotor. Specifically, we think that the not having a treadmill during exploration spaceflight is going to be pretty impactful. So this is our balance training countermeasure that we're using right now. We actually call it our proprioception training countermeasure, and we're trying to keep these contributors to balance function. We're trying to keep them conditioned during spaceflight. This is a ground and a ground version of it. So we have subjects lie on their backs on an air-bearing sled, so they kind of glide like an air hockey puck, and they get pulled down onto this tilt board. That way they can do the task like we imagine it for crew members. So you can see here, they're looking up at a monitor that's above them. They're controlling a cursor using a board that they're standing on. And so we're directing them to tilt the board, to move the cursor, to capture different targets. And of course, we can place those targets in an infinite number of ways on the screen in front of them to get them to really move through those different ranges of motion and stimulate their proprioception system. We have now started to evaluate the efficacy of this countermeasure in head-down bed rest. So I don't know if folks here are familiar with bed rest as a analog for spaceflight, but basically you get the body unloading at the legs and the feet, which kind of simulates the proprioception deconditioning that occurs during spaceflight. And then you also get the headward fluid shifts that mimics the cardiovascular adaptations and SANS and whatnot. So we are currently right now getting ready for campaign 2 of testing this countermeasure in bed rest. So we're trying to get more data on how well it works. So far, the results are pretty promising. We're in parallel developing an in-flight version of this. So this is a picture of us testing it in parabolic flight. It's the same idea of where we're pulling someone onto a tilt board and having them do these different tilting tasks. The parabolic flight demonstration was actually pretty successful, and so we're now going through development for hardware to be put on the ISS. We hope to do this ISS demo before the end of ISS, and then that way we have the hardware evaluated, and then hopefully we have the efficacy of the countermeasure evaluated in bed rest, which will help us move forward with a flight study, probably in a commercial low Earth orbit environment or gateway. Okay. We're also right now developing some sensorimotor assessment tasks. So if you think about it, when you land on the moon or a Martian surface, we need to have some type of test to tell us whether the crew member is ready to perform their operational tasks or whether they need additional rehabilitation before they go out and do their EVA. So we partnered with different universities to come up with various tasks. And what we've been doing over the past couple years is kind of validating these tasks using different analogs. So one of the analogs is 3GX centrifugation, which we talked about before. It can kind of produce similar disorientation that the crew members experience. And then we've also been using ground versions of spatial disorientation to help validate these tasks. We had crew members come and try these tasks and try these analogs as well, and we did get very positive feedback from that. So we're hoping to eventually, kind of test these in parabolic flight and then eventually test them during the Artemis missions. That way we can start to come up with actual performance thresholds that tell us when a crew member is or is not ready to go onto EVAs or other operations. So it's informing what we call NASA standards. Okay. This next study, I was just looking at the time.
Oh, don't worry about it.
We're good? Okay.
Yeah, doesn't matter.
Okay, there's only a couple more. Pre-flight sensorimotor training is another countermeasure that we're really interested in right now. So a lot of this work was done back in the early 2000s, where this idea of sensorimotor adaptability first came to be. And really, they looked at it through the use of visual distortion. So remember, you have those, your visual, vestibular, and somatic sensory systems. You can kind of manipulate those senses in all different ways. So what different groups did is they had different visual distortion lenses to see how well people can adapt to visual distortions. So you can use lenses that flip your environment upside down. You can have it shift your environment so that you're looking, to the left or to the right. You can have it cross your vision. And basically what they found is that, one, yes, you can adapt to your new visual environment, whatever that new environment is. But Also, by training you to adapt to that new environment, you can better adapt to a new environment that you haven't experienced before. So if you train someone to adapt to the goggles that, cross your vision, you can better adapt, more quickly adapt to goggles that flip your vision upside down. Okay. That was kind of the idea, and it led to all these different proposals for sensorimotor adaptability, where we can put crew members on a treadmill and project a hallway that they walk down. You can sway the hallway visually, just using the projector system. You can sway the treadmill that they're walking on to impart those proprioceptive perturbations. But basically, the challenge that the lab ended up running into is just, again, the size of equipment that was needed, the expertise that's needed to run the equipment, how hard it is to get into crew schedules, because ultimately this type of pre-flight training would likely need to be implemented by someone like the astronaut strength and conditioning team that already has time with the crew members for pre-flight conditioning. Yes, question.
So your EVA astronauts do a lot of virtual reality training to train on tasks.
Mm-hmm.
And they also do a lot of training in the pool, which would also be standing on your head inside of the spacesuit. Have you ever specifically separated those high timers who train in those environments and look at that, like you said, visual training with both virtual goggles and in the pool? Is it all helpful? Is there any correlation there?
Yeah, so for those online, the question was, primarily about how much training the crew members have gotten in these different environments, like the NBL and whatnot.
And those are a subset of the astronauts that, your pilots and your co-pilots until recently never ever trained for EVAs. And some of your robotic arm operators never train. But the EVA guys train all the time in that virtual reality and in the pool.
Yeah.
So they would have a different background going into orbit. And I just, they might, if you isolated them from the population, would there be any significant difference?
Yeah, and I think the answer is just that really we haven't been able to do that type of analysis. I mean, it's a really good idea. I think one thing we'll need to figure out is how do we quantify different levels of training and types of training. I mean, you could just bucket people into, these people have done this type of training, these people haven't.
Yeah, it'd be a little more difficult because ISS is training a big portion of their population to do EVAs.
Yeah.
Where the shuttle in a crew of 7, you'd have maybe 4 out of the 7 would be trained to do EVA and the other 3 would not.
Yeah. Yeah. So, it's a very good idea, and it's something that we need to look into a little more.
Astronauts actually had a cadre of EVA for shuttle.
Yeah.
So they don't have that. So basically, it's something you don't have a requirement then for an EVA trained individual on a particular flight or assembly.
You have some primary folks, but most of the folks on ISS are capable. You got a few that are going to be robotics, and you got a few that are designated to do certain EVAs, but there isn't quite as definitive. For this mission, you're going to do this, and for this, and these people will do this. On ISS, there's more of a jack of all, master of none kind of thing.
Yeah. Post assembly, then that makes sense.
Yeah.
Yeah, and there can be other backgrounds and trainings for the crew members as well. Some are pilots, some are scientists, or
When you haven't addressed male versus female.
Yeah, so actually, I mean, it's for ours, there's really not that much difference. So even I think in the motion sickness one, I'm not gonna go all the way back. The green and the blue, we actually did a comparison there of male versus female. We didn't see any differences in sex.
So on orbit, space sickness, equally random, male and female.
For the most part, yeah, we don't see major differences. Some of the other risks do, but for sensorimotor, it's pretty similar.
Question.
Yep.
I seem to remember that the Russians actually did Soyuz training on board station. This is going back like 20, 30 years when I was working the station.
Uh-huh.
Are they still doing that? Is there any correlation of the data of their training on board with being able to do the tasks that they actually needed to do? You know, for let's say returning a Soyuz back in manual control.
I'm not familiar with what the Russians are doing,
Okay.
but we are working with the current, HLS group. Where is it? For our current manual piloting study. So we do have this onboard training component for those, the skills-based risk, I guess you could say. And we think that, this can be considered like a countermeasure for, this manual control risk of trying to land the vehicle. We need their skills to be fully trained up going into that event.
We don't have any data for correlation yet.
Not that I'm aware of.
Okay.
So
Over the years, a long time ago in a country far, far away, crews were not famous for wanting to participate in a lot of this stuff. How's that going today?
Pretty good participation. Yeah, we have. I don't know what the exact numbers are now compared to back then, but I'd say most of the crew members are participating in some science. We do have big complements of research studies. I don't know if you've heard of Cypher, but
So they still sign up for the study though, when they fly.
Mm-hmm. Yeah. We go through a whole informed consent briefing, and then yeah. Okay, the last just comment on this slide is, one thing that we're working towards a little more is what if we can provide that pre-flight training with this very simple vestibular disruption tool. So it's called galvanic vestibular stimulation. We do actually use it as an analog of spaceflight, or an analog of the disorientation you experience post-flight. But can we also use it then to train a crew member to perform better when they, go through G transitions? So we know on the ground that, just regular healthy participants, they, at first when they wear this electrical stimulation, they do get disoriented. Their balance does get impacted, but after, a few weeks or a few times of using this, they can improve their balance performance in the face of this vestibular disruption. So we are interested in, testing this a little more using maybe some other ground analogs to validate this. And then eventually this would be something very small and simple that we could get the astronaut strength and conditioning team to implement in their current pre-flight conditioning programs. Okay, last two countermeasures to mention. They're more crew egress countermeasures. So one is an Earth-fixed visual reference. It's all about providing these external cues to the crew member, kind of like how the pilots will have these different instruments in front of them. What other external cues can we provide to a crew member while they're performing, an egress or an EVA? So you could see the green line here that's projected. That kind of just gives a reference to the horizontal, so then therefore also gives a reference to the direction of gravity. And so we've seen some positive results with that, helping improve posture and performance during different functional tasks. And then another countermeasure is variable tactile feedback. So basically something that can vibrate at different amounts based on how much you tilt relative to gravity and in what direction. So that, may be a helpful countermeasure for all different scenarios, like, controlling a vehicle, balance, locomotion, etc. So those are just a small subset of things that we're working on in the lab right now. I appreciate all of the questions, and I'm happy to answer any more questions if you have them. Yes.
So spacecraft design.
Uh-huh.
Have you done any work on, most buildings, the ceiling's white and the floor is a dark color because we get it dirty with our boots on, and the lights are usually up in the ceiling as opposed to on the ground. Is there any work to try to drive a certain orientation with paint schemes, light schemes, designs to say, we want you to stay oriented to your environment, so we're going to make it not like the space station where everything's symmetrical on all axes kind of thing?
Yeah, no, we have had some conversations. It's primarily led by the human factors groups, so we've talked with them a little bit. I mean, the biggest thing that we try to push for is for safety things like handholds and stuff, so that when they do land and they hopefully do have a vertical orientation reference, but also they have the safety handholds and catches for them in case they do experience instability or need to catch themselves from a fall. But yeah, probably don't go into the level of detail as what you're saying with the color of the floor and the ceiling.
Yeah.
Any other questions?
There's still seem like a lot of unknowns still.
Yeah, a lot of unknowns. I showed just a small subset of countermeasures, but there's been a lot of countermeasures over the years that have been proposed. They've been kind of developed a little bit, and then run into some issue here or there with either the technology is not ready to implement in flight, or it's not operationally feasible. And so we have a long list of other things that maybe one day we can revive when the technology gets there. Yep.
So it all seems to be, I want to say, motor, physical, hand-eye coordination kind of things like that.
Yep.
With all of the AI tools for voice recognition, has there been any attempts to now move away from? I know that you talked about automation, but now voice control of things to actually do some command control to help bypass the hand-eye coordination issues with, say, manual control kind of operations.
No, that's a great idea. I'm sure someone's working on it, but no, we haven't specifically looked into it. I mean, we have been using other environments like augmented reality, for example, so that they're not actually having to interact with things. It's more augmented, virtual for them. But voice is one that we haven't really looked into much, but I'm sure the human factors people have started to. Do you have another question?
So in many of the popular science fiction movies over the years, we've seen the giant space stations like wheels and, the transit vehicles going with a centrifuge kind of, arm out pivoting around. And, it's hopefully to adapt to the loss of 1G and our muscle atrophy and all that. But in all those cases, now you're gonna have these inner canals, the fluid's gonna be spinning around. So it looks to me like if you did that, you might, solve the muscle and the bone problems, but you're still gonna have that vestibular conflict because your ears are gonna say, I'm doing a somersault, once a minute.
Yeah.
But maybe my G is oriented towards my feet now, so.
Yeah.
What would that do to you? Have you ever tried any kind of studies or looks at what it would take if you did put a centrifuge on a trip to Mars?
Yeah. Yeah. So the question for those online, it was, primarily about centrifugation and artificial gravity, but what other side effects there could be with that. So there has been some artificial gravity studies where, centrifuging people, and that was tested during bed rest. So it was to see, like you mentioned, if it can help mitigate those declines in muscle balance and whatnot. I think part of the issue they ran into was under prescription of the artificial gravity because of the motion sickness and other dizziness that they were concerned about. Those of you that might be pilots in here, you might be familiar with like the cross Coriolis effects that you might experience when you're being spun, and that can kind of lead to that motion sickness and dizziness. So yeah, there's still a lot to kind of figure out there. The artificial gravity itself seems like it would be promising, but I totally agree with you that there's still a lot, not just from the motion itself causing sickness, but the visual. I know there's some commercial companies right now that are looking to spin, but they want to have windows too, and we think that could have some disorientation or dizziness problems of seeing the visual surround constantly moving like that. So
another question online. Maybe if you're ready. I recall there was maybe some biofeedback experiments and tests done in the 70s, perhaps. Has anything come out of that, and any other biofeedback things at least for the motion sickness or other effects?
Yeah, biofeedback training is still kind of ongoing. It's not operationally implemented though, to my knowledge. I mean, I think it's something that's encouraged for the crew members, but it's not part of their actual training right now. And for those that aren't familiar with biofeedback training, so for example, it's say looking at your heart rate and trying to calm yourself down purposely to get your heart rate to go down. That's kind of the the simple version of biofeedback training that crew members may or may not be doing right now.
So was that shown as being effective, or just not really that effective, or not? Is that why it's not in the current training?
I think it's effective, but it just doesn't have quite the level of impact to be a high priority, I guess.
Okay, thank you.
Anyone else? All right, well, Tim, thank you very much.
Thank you.
That was very interesting. Very interesting. Thank you so much for taking the time to brief us.
Yeah, thanks for having me.
Oh, so David, I guess you can take down the recording now. But yeah, all right. It's amazing. It's really amazing the things we know and the things we don't know.
Yeah.
Sounds like you've got good job security though.
Yeah, we'll see. But yeah, so my email was there. So if anyone has any